Hello everyone and welcome back to my channel. I am Sahil Sawant and currently I am pursuing my M.Tech in computer engineering here at VJTI Mumbai, and I have a strong background in electronics and telecommunication engineering and some research experience in RF systems and radio astronomy. In this ongoing series, we have discussed in episode 1 that signals are variations that carry certain amount of information. In the second episode, we studied how Fourier reveals hidden frequency structures. In the third episode, we moved on to incorrect sampling, which causes aliasing. In the fourth episode, we looked how finite observations can cause spectral leakages. In the fifth episode, we saw how noise is unavoidable and SNR, which defines our system performance as well. Today, we move on from analysis to designs, and today's topic is going to be filters and engineering trade-off between FIR and IIRs. Now, let's ask ourselves this simple question. Why do we exactly need filters? We need filters because in real systems, signals can mix with noise. Multiple frequencies can coexist at the same time, and systems have certain bandwidth limits as well. A filter allows certain frequencies to pass and it suppresses some other frequencies. Like for example, an audio equalizer or RF bandpass filter. We also have ECG low pass smoothing filters, and we also apply anti-aliasing filter before we connect our ADCs. Filters are the components that shape the signals. Now we will look at some basic types of filters. Before we start with FIRs and IIRs, let us classify the filters on the preferences of their behavior. First of all, we have low pass filters, where we pass some low frequencies. We have high pass filters, in which we pass few high frequencies. We also have a band pass filter, in which we pass a particular band of frequencies. We also have band stop filters, which rejects a few or certain frequency levels. That's what we call some functional classification. Now we go into some deeper structures, in which we will study about structural classification. First of all, we will start with FIRs. Now, FIR stands for finite impulse response. This means if we apply a certain impulse input, the output settles to zero in finite amount of time. Mathematically, output depends on current and past inputs. There is no feedback in FIRs. Mathematical structure of FIRs is defined as y of n equals to sigma or summation of b of k into x of n minus k. And important characteristics that we need to study about FIRs are, it is always going to be stable. FIRs can achieve exact linear phases, and usually FIRs require more coefficients than the IIRs. Linear phase means all frequency components are delayed equally. This preserves the waveform shape. That is important in audios or biomedical signals or even in data communications. Now let us look at IIRs. IIR stands for infinite impulse response. If you apply an impulse input, output theoretically continues forever. Why? Because IIR uses a certain amount of feedback, and output of IIRs depend on current input, past inputs and past outputs as well. The mathematical structure of IIR is given as y of n equals to sigma, that is summation of b of k into x of n minus k, as it was in FIRs, plus we also add negation of a of k into y of n minus k. Because of feedback, IIR can achieve sharp filtering with fewer coefficients as well. Now let us look at advantages of IIRs. IIRs are computationally efficient and they require low order. They also have faster roll-off between the signal and noises. But they may become unstable over a particular amount of time and typically do not have linear phases. Now let us look at the property of stability. FIRs are always going to be stable, whereas IIRs can be unstable sometimes. Moving on to phase response. FIRs are linearly possible, whereas IIRs are usually non-linear. Moving up to complexity, FIRs have high order of complexity, whereas IIRs have low order of complexity. Looking at efficiency, FIRs are computationally more slower, whereas IIRs are computationally more faster. So, which one is better? This is the wrong question. The correct question that engineers have to ask themselves is which one suits our application better. Engineering is about contexts. In audio systems, waveform shapes matter. Phase distortion can lead to change in sound quality as well. So FIR filters are preferred when linear phase is important. But in real-time embedded systems, what we do is, let's say memory and CPUs, both are limited. IR filters are computationally more efficient. So embedded control systems often use IR filters in their applications. In radio frequency systems, analog filters are more often, like they show IR-like behavior. But in digital baseband processing, may use IR filter for efficiency. But compared to data transmission lines, pulse shaping often uses FIR filters. Because linear shapes or linear phases prevents symbol timing. Again, there is a certain amount of trade-off between both the filter types. Now, here is something more important that we as engineers need to understand. IIR filters have poles. If poles lie outside a unit circle, the system is going to be unstable. Output grows without a bound, and that is something that is not theoretical. Improper coefficient design can break the real systems. FIRs, on the other hand, don't have this particular issue. They are inherently stable. Sometimes safety matters more than our efficiency. From implementation view, what we saw is that FIRs have more multiplications. They use more memory and parallelizably easy. In IIRs, they have fewer coefficient. They do have feedback loop, and they are sensitive to numerical precisions. In fixed point systems, IIR rounding errors may accumulate over a certain amount. Designers must consider hardware limitations as well before deciding which type of filter they are stable with. If you remember one thing from this video, remember that FIRs and IIRs is not about which type of filter is superior. It is about understanding the system requirements and then choosing among themselves. Do you need linear phase? Do you need guaranteed stability? What is the low computational cost for the system? And what is a fast roll-off between both of them? Your answer determines the filter choice that you are going to take. That is what is engineering thinking. In the next episode, we go a little bit much deeper into something more fundamental. Convolution system and system response. Because filters are just systems, and convolution explains how systems shapes the signals. Welcome back again to Signals and Systems. Hello everyone and welcome back to my channel. I am Sahil Sawant and currently I am pursuing my M.Tech in computer engineering here at